Hey guys, this is me Rakesh Aarya, your chemistry mentor. You know me by now. This is the lecture 4 of thermodynamics, and I hope you guys enjoyed lecture 1, lecture 2, lecture 3. Like every lecture we have a concept section, we have an application section, and we have a self-simulator section where we try to catch your mistakes. And similarly, following the trend, we'll do the same in lecture 4 of thermodynamics, and we'll try to make thermodynamics a little more fun for you. Let's get right to it. Lecture 4 of thermodynamics. To start with, recap of first 3 lectures. We discussed about internal energy. We discussed that internal energy is a sum of kinetic energy and potential energy. Now you might ask, what exactly is kinetic energy? Because in our perception, kinetic energy is mostly related to, say, velocity. Say we have a block over here, and this block moves with some velocity v. Then kinetic energy is simply half mv square. But as you read more in class 11th and 12th, you realize that kinetic energy is not only related to translation. This is translation. This is translation simply because I can write it on this board. If I go up, this will be my velocity in y direction. This will be my velocity in x direction. But not only velocity in x, y, and z direction. Z direction would be outside the board, coming towards you. But kinetic energy is also related to translation and rotation and some other things as well. So kinetic energy is, this formula seems very simple, but it can be quite complicated when it comes to exact calculations. So kinetic energy involves both translation as well as rotation. Not only that, it also includes vibration. It also includes some other factors which are not important at room temperature. The 2 factors which are important at room temperature are translation and rotation, and we are going to focus on these, as well as there is some potential energy also involved. If I was to sum up what internal energy is, it is the energy, it is the sum of energy of a particular system, all kinds of energies that you can include inside it. There are certain kind of energies that don't change. For example, if I'm standing here, I have a certain potential energy with respect to the sun. Why is that? Because the sun exerts some gravitational force on me, and as a result, I have some potential because of gravitational energy of sun. But that's not going to change much. That's not going to change much if I move from this side of the board to this side of the board. Because I'm already so far away from the sun, moving 1 feet, 1 meter, doesn't matter that much. So we're not going to count many energies over here. It's not our job to define U absolutely. It's not our job to define U absolutely, but it's our job to worry about delta U. That if I do something to my system, if I move around over here, what exactly changes? If I heat a system, what exactly changes? So our job is to focus on this quantity delta U and not on the absolute value of internal energy, which is written in the second point. U need not be defined. Internal energy absolutely need not be defined. What matters is delta U. Delta U matters. Change in potential energy matters. In many textbooks, you will see it written as a limitation of thermodynamics, but I don't count it as a limitation of thermodynamics. This is what thermodynamics intends to be. This is what thermodynamics aims to be. Thermodynamics aims to study the changes in a system. Thermodynamics doesn't care too much about the potential energy with respect to the sun, potential energy with respect to some distant planet, potential energy because of the light in this room. We only care about delta U, things that matter, things that change. If I do a chemical reaction, what is going to change? My reactants are going to turn into products. That has nothing to do with the sun. Maybe it does have something to do with the sun. Maybe my reaction is photosensitive. Maybe my reaction occurs under sunlight. In that case, I have to worry about the sun. But if I don't have to worry about the sun, which is usually for most reactions, then I only need to care about delta U. Next point, very important point. I've written du isolated equals 0. From starting, we have been solving some questions. We have been discussing some concepts regarding change in internal energy of isolated systems. Change in internal energy of isolated systems. And you must have written down that delta U equals 0. That delta U equals 0. Change in internal energy equals 0. This is true for isolated systems. But we discussed in last class that delta U means large changes. Delta U means U final minus U initial. It means that if I add 10 liter to something, then the change in volume is 10 liter. But in case of an isolated system, it's not just the large changes. Even the small changes matter. If I like to draw a diagram over here, if I like to draw P versus V, if I have two states, A and B, and actually let's just forget about the second state. Suppose that I take a cyclic path back to A. In this case, delta U equals 0. Why is delta U equals 0? Because the initial and final state are same. So if I do U final minus U initial, U final is also A, U initial is also A, and hence my delta U is 0. But this is not an isolated system, because during the path I reached many points. I reached this point. I reached this point. I reached this point. Point number 1, point number 2, point number 3. And internal energy of point number 1, point number 2, point number 3 may be different from internal energy of point A. And as a result, my internal energy changed during the process. It changed while going from A to 1. It changed while going from 1 to 2. It changed while going from 2 to 3 and 3 back to A. But for an isolated system, internal energy cannot change even a little bit. So that's why we write du equals 0. Du equals 0, not delta U equals 0. So that even small changes, so that a system at A can't even go to a small place over here, can't even go to a small distance over here, can't even go to a small distance over here. All these are not allowed. All these are not allowed for an isolated system. For an open system, for a closed system, internal energy can change. Open system can exchange both mass and energy. Closed system cannot exchange mass, but it can still exchange energy. And as a result, internal energy can change. But internal energy of an isolated system can't even change a little. That's why instead of writing delta U equals 0, which is wrong, we write du equals 0. Du of an isolated system equals 0. Let's move on to the next step. U equals 3 by 2 nRT. Let me just clear the board so that you guys can look at it clearly. U equals 3 by 2 nRT. I asked you to remember this formula. This formula is only true for monoatomic gases. This is not true for diatomic gases. Examples of monoatomic gases are helium, neon, argon, all noble gases. If you put them in a chamber, pure state, they are monoatomic. But we can have diatomic gases like nitrogen. We can have diatomic gases like hydrogen, H2N2. We can have diatomic gases like oxygen. We can even have polyatomic gases like H2O, water. If I heat up water to a temperature greater than 100 degrees Celsius, then it's steam, and steam is a gas. I can have carbon dioxide. Carbon dioxide is also a gas, and it has more than 2 atoms. So for all those cases, U is not equal to 3 by 2 nRT. U is not equal to 3 by 2 nRT. It's only true for monoatomic gases. Only true for monoatomic gases. Moving on, we discussed about heat, we discussed about work, and we discussed about the fact that heat and work of a state are meaningless. It does not matter what heat or work of a state are. Not only does it not matter, it is not defined. I can't take a system and ask the question, what is the heat of the system? What is the work of the system? And why can't I ask that? It's because heat, work are path variables. Heat and work are path variables. If I like to draw a graph, once again, we always draw state variables on the axis. Pressure over here, volume over here. You can do temperature, you can do number of particles as well. Going from A to B via some path. I can go through this path, I can go through another path. Any kind of path if I go through, I can talk about the heat and work of the paths. I can talk about the heat of path 1. I can talk about the heat of path 2. I can talk about the work of path 1. I can talk about the work of path 2. But I can't talk about heat and work of state A. I can't talk about heat and work of state B. Heat and work are related to path, not to state, right? Heat and work are path variables, they're not state variables. Unlike internal energy, unlike pressure, unlike volume, unlike temperature, unlike number of particles. I can define all those things for state A. I can define U, I can define pressure, I can define volume, I can define temperature, I can also define number of particles. I can do the same for B, I can do the same for B, but I can't define heat, I can't define work for state A and state B because heat, work are path variables. They are not state variables. So never answer the question, never ask the question, what is the heat / or work of any particular state. They are meaningless questions, they're not defined. Another thing we discussed about is work equals area under PV graph. Area under PV graph. It's an intuitive application. This point should be point number 7. Sorry about that. Point number 7 is work equals area under PV graph. We discussed about the mathematical formulation of work. We discussed that work is the dot product of force and displacement. However, in case of thermodynamic systems, we don't come across force that much. If you have been following lecture 1, lecture 2, lecture 3, I might never have mentioned a force of a state. I only talk about pressure of a state. Pressure is related to force because pressure times area gives force. So what we did was we formulated the pressure definition of work. We formulated. So work equals area under PV graph. So just to revise it and keep it all in your mind, I'll draw the diagram one more time. Once again, this is 7th point, not 6th point. So if I draw pressure, if I draw volume, one thing that some people tend to miss or not mention is that this pressure is supposed to be external pressure, right? This is supposed to be external pressure, and regardless, it does not matter, and we will come across this point in the upcoming lectures. It doesn't matter in class 11th and 12th whether this is external pressure or internal pressure. If we are going from state A to state B, then work done is given by the area under this graph. Work done is given by this area. We also talked about the fact that area during expansion is negative. Why is area during expansion negative? Because if the system pushes on the surroundings, system is expanding. If the system is expanding, it is pushing onto the surroundings. If it is pushing onto the surroundings, then it has to do some work. And we know the first law of thermodynamics says delta U equals Q plus W. And now let's forget about Q for a second. Let's only focus on work. In case our system pushes onto the surroundings, then it has to do some work. It has to use its own energy to do work. And as a result, the energy decreases. If the energy decreases, then work should be negative. Similarly, work done during compression, work done during contraction, work done during deflation, all of them are positive. Why? Because the surroundings is doing work on the system. It is compressing the system. When it is compressing the system, it is adding the energy. It is adding the energy. We talked about it. We talked about our parents scolding us. Our parents scolding us is like them putting pressure on us. See, that is not a bad thing. That increases our energy. When surroundings do work on us, that increases our energy. And it is our job to use that energy in a fruitful way. Thermodynamics tells us that we can use the energy either using heat, which is not very useful. What are you going to do with heat? Or using work. Work is very useful. You can run cars using work. You can run trains using work. And when it comes to this example, you can clear the exam using work. So when your parents scold you, take it as a positive thing. Take it as that your energy has increased and now you have more energy to spend to do work. Moving on. What are we going to talk about today? We're going to talk about some types of processes. Different systems can do different things under different conditions, right? We have to classify those things. This is a classification problem. Types of processes is a classification problem. We have to classify them so that we don't have a misunderstanding. Another reason we have to classify them is because when the question is asked in the exam, they're going to mention these things, and so that you're able to answer those questions easily and get a good rank, right? That's a short-term goal, but in the long term, remember, we classify things so that we're clear on that. So that somebody sitting in Germany who doesn't speak English very well, for whom English is not a native language, we're clear when we say what type of process our system is undergoing. We're going to talk about heat capacity. You must have already read about heat capacity in 9th and 10th. I highly recommend that if this concept is not clear in your head right now, if you can't remember what heat capacity is, I highly recommend after this lecture, you go back and look at the heat capacity chapters in 9th and 10th class. In case it's not there in 9th and 10th class, then just look it up online. Look at a few videos, look at a few intuitive explanations. I understand that I can't show everything on this board, but there are a few good videos out there. There are a few good resources out there that you can search very easily. Just search on Google about heat capacity and refresh this concept. We are going to talk about it nonetheless, but if I fail to make you understand what heat capacity is, please by all means search for it, work towards it. Ask your questions, ask your doubts in comments, and I will be sure to clear it. Moving on, we'll be talking about equipartition of energy, a very important concept, a very interesting concept. I could talk about equipartition of energy for hours. Unfortunately, I don't have that time. It's such an interesting concept, equipartition of energy. All right, let's start. First, I just want to revise state and path functions one more time because very important. Sometimes questions are asked directly from this. IIT-JEE Mains, IIT-JEE Advanced, AIPMT. Sometimes they'll ask, what is a state function? What is a path function? And if you don't have those concepts clear, you can't, not only can you not answer that question, but the whole thermodynamics becomes confusing. So let's just go ahead. Right, state functions defined by the state. State functions are defined by the state. If I take a snapshot of my system, I can answer every question related to state functions because they're only defined by what state the system is in. Path functions, on the other hand, are not defined by the state, they're defined by the path. Just like we talked about heat. Heat is a path function, work is a path function, state functions, internal energy is a state function. So if I would like to draw the graph, going from point A to point B, at each of these points, at any point during the path from A to B, I can choose another point C, I can choose another point D. At each of these points, I can define my state functions, I can define my state variables. However, path functions are only defined for the entire path. I can't talk about heat of A, I can't talk about heat of C, I can't talk about heat of D, I can't talk about heat of B. I can't talk about all those things because heat, work are path variables and path matters. Path matters a lot in thermodynamics. You will soon come to realize different paths. We are going to talk about types of processes today. Different paths have different properties, and as a result, path matters. So state functions are defined for any given state. Path functions are defined for a process. You need to have a component of time inside it. Something is changing with time, right? Moving on. Let's talk about types of processes. The first first classification is based on thermodynamic conditions. What are thermodynamic conditions? Thermodynamic conditions relate to thermodynamic variables: pressure, volume, temperature, number of particles, entropy, enthalpy, all those things. So I'm going to relate types of processes based on thermodynamic variables. I'm also going to relate types of processes to speed of the reaction. But we will discuss that in lecture 6. This is regarding reversibility, irreversibility of any given reaction. This might seem slightly confusing because most textbooks mention that thermodynamics does not concern itself with speed of reaction, but in a certain way it does. In a certain way it does, and we are going to find that out soon. The first type of process that we are going to discuss is isochoric. First of all, you need to remember that this term iso means same. Not only does it mean same, it means same throughout. It means same throughout. Throughout any given process. Remember, we're discussing types of processes, not types of state. We're discussing types of processes. Since we're discussing types of processes, it's same throughout the process. All the time the process is being carried out, iso means whatever quantity we're going to discuss is going to be same throughout the process. And isochoric, this term over here, same throughout. What is same throughout? Volume. Volume is going to be same throughout in an isochoric process. How do I show it on a graph? How do I show it on a graph? This is my pressure axis. This is my volume axis. Simple math. If I move towards right, my volume increases. Right? If I move in this direction, my volume increases. If I move in this direction, my pressure increases. However, if I want to keep my volume constant, if I want to have an isochoric process, I can't go right because my volume increases. I can't go left because my volume decreases. I can only go up and down. So what does an isochoric process look like? It looks like this. Going from point A to point B. Point A to point B. At this point, I want you to pause for a second and really visualize this happening. I can either go up, I can either go down. Both are isochoric processes because volume is not changing while I'm going up and down. At the same time, I want you to answer one question. I want you to try and answer one question. You might not be able to answer it. It's all right. You might not be able to answer it, but I want you to think about it. What is the work done? What is the work done during an isochoric process? We will come back to it later, but take a moment, pause the video and just think about it. What is the work done during an isochoric process? Moving on, isobaric. Once again, iso means same throughout, and baric, you can actually guess what baric means. There's a unit in thermodynamics that relates to this word baric, and that's bar. Bar is the unit of pressure. So this time, what is going to be same throughout? It's going to be pressure. If I try to draw it on a PV graph, I can't go up and down because I'm going to change the pressure. I can only go left and right, A to B. I can either go towards right, I can either go towards left. Going towards right, I'm increasing my volume. Going towards right, I'm increasing my volume from a low volume to a high volume. Going towards left, I'm going to decrease my volume. That is compression. If I go towards left on a PV graph, I'm decreasing my volume. That is compression. So isobaric means this whole process, the pressure is same. And what is the quantity of pressure? Whatever this value over here is, this is the quantity of pressure. This pressure is going to be constant. So during an isobaric process, pressure stays constant. You can go either right, you can go either left. Going towards right, it's called expansion. Volume is increasing. Going towards left, going towards left, it's called compression, volume is decreasing. Next is isothermal. What do you suggest this is? Iso means same throughout. Thermal means temperature. Thermal means temperature. So during my isothermal process, my temperature is going to stay the same. I have a PV graph over here. Take a moment, think about it. How do I show constant temperature on a PV graph? It seems very difficult. But think about it. And I'll give you a hint. Think about it in terms of ideal gases. How do I keep temperature constant for ideal gases? Take a moment, pause the video and think about it. All right. Ideal gas law. What does it look like? Ideal gas law looks like PV equals nRT. And in this law, if you keep temperature constant, then take a look at it, the right hand side is constant. For a closed system, number of particles does not change, R does not change, and in an isothermal process, temperature does not change. So this whole side is a constant. As a result, my equation becomes PV equals constant. PV equals constant. For an isothermal process of an ideal gas, PV becomes constant. PV becomes constant. PV becomes constant. Now this equation you will come across in mathematics. This is a very well-known equation of a hyperbola. It's a very well-known equation of a hyperbola. If you can't relate to it, you will see this equation xy equals constant. Hyperbola it exists both in first quadrant and third quadrant. Unfortunately, in terms of physical variables, I can't take negative volume, I can't take negative pressure. So I only keep it in first quadrant. And what does PV equal to constant look like? It looks like something like this. Going from state A to state B, an isothermal process looks like a curve. Right? It looks like a curve. So this is my PV equals constant isothermal process. That's one kind of a process. Next type of a process that we can talk about. Isothermal process, I want to talk about it on a different scale. Temperature versus anything. You can take any other variable, pressure or volume. In this scale, what will isothermal process look like? Since I have temperature over here, I can move in this direction from A to B, from A to B. In this direction, either I can go towards right, I can go towards left. I'm not changing the temperature because I'm moving perpendicular to the temperature. If I'm moving along the temperature, I change the temperature. But if I move perpendicular to the temperature is in like up and down direction. If I move left and right, I'm not changing the temperature. It's an isothermal process. The next type of process is isoentropic. It's a very nice name. You must have heard entropy time and again during your lectures. Isoentropic means, iso means same throughout as always. Entropic means same entropy throughout the process. And we are going to relate it to heat. Because an isoentropic process is also known as an adiabatic process. An isoentropic process is also known as an adiabatic process. There is no transfer of heat during the process. So isoentropic process, another name for this is adiabatic. And we already know what adiabatic walls do. They don't allow exchange of heat. And as a result, heat exchange is zero. You can call it adiabatic, you can call it isoentropic. You should remember both the names. On a PV graph, it looks very similar to an isothermal process. I can go like this, A and B. So how do I differentiate between an isothermal and an adiabatic process? If you're expanding, isothermal process goes above. If you're compressing, isothermal process goes below. So you have to remember this kind of a graph. If you're expanding, this is my adiabatic process. I'm going to write AD over here. This is my adiabatic process. And this is my isothermal process. I'm going to write IT over here, isothermal process. So if you have to differentiate between an isothermal process and an adiabatic process using a graph, simply see during expansion, the process going below is adiabatic. During compression, the process going above is adiabatic. Moving on, isoentropic process on an entropy scale, S. The first time you've come across this variable, S means entropy. S means entropy. We're going to talk more about this, but just like isothermal process, if I plot entropy on the y-axis, on the axis that goes down to up, if I move perpendicular to it, left to right, I'm not going to change the entropy. So I have A to B. I can either go right, I can either go left. Either way, it's an isoentropic process because the entropy is not changing. Now we're going to talk about heat capacity. Heat capacity is also represented by the symbol C. You have come across heat capacity in your earlier classes. We're going to talk about it in more details right now. So at this point, I want you to do a thought experiment of heating a block. Take a block, room temperature, minus 100 degrees Celsius, plus 200 degrees Celsius. I don't care where you start. But take a block and start heating it or start cooling it. Right? That is the thought experiment. One of the things I like about saying thought experiment is it makes you feel so smart. Like, I don't know. If one of these days you're just lying down resting and your parents come and ask you, why are you not studying? Your exams are coming up. You can just tell them, I'm doing a thought experiment. It just makes you feel so smart. I love saying thought experiments. In fact, many discoveries in physics were based on thought experiments. They were not based on real experiments, but somebody just imagining some experiment and deducing what the result of that experiment is going to be. All right, so heat capacity. Let me just refresh your memory on heat capacity. Heat capacity is the heat required to raise the temperature of body by 1 unit temperature. 1 unit temperature. This unit can be anything. This unit can be Fahrenheit. This unit can be degree Celsius. This unit can be Kelvin. Those are questions about units. Those are not questions about concepts. But in general, we talk about the Kelvin scale. We want to raise the temperature 1 unit on a Kelvin scale. We want to go from 200 Kelvin to 201 Kelvin. We want to go from 373 Kelvin to 374 Kelvin. And if you are observant enough, in this process, water has boiled. 373 to 374, water boils. Under normal atmospheric condition, what is the boiling point of water? If you can quickly recap it, the answer is 373.15. It relates to the Kelvin degree Celsius conversion scale, that if you have a temperature in degrees Celsius, 100 degrees Celsius for boiling of water, you want to convert it into Kelvin, then you just add the number 273.15 to it. So 100 plus 273.15 is 373.15. So water boils at 373.15. And if I take water from 373 to 374, water has boiled. And a lot of interesting things have happened in that one unit temperature change. A lot of interesting things have happened. How can I tell this? The physics you're reading right now cannot explain what happens during that boiling of water phase. It can explain what happens during boiling of water phase under normal conditions, but under conditions like high temperature or very high pressures, the physics that we are reading right now cannot explain that. There's so much fascinating discoveries just relating to heat capacity, and Let me just move further. We don't have a lot of time. You will discover them later in your graduation. So heat capacity. I said heat capacity is the heat required to raise the temperature by 1 unit Kelvin. All right. So if I have a block, I'll just clear the board to make space for writing this down. If I have a block, it will have some heat capacity. It will have some heat capacity. And if I supply heat equal to the heat capacity, numerically speaking, if heat capacity's numerical value is 200, if I supply 200 heat, then I'll raise the temperature by 1 joules. So if I supply Q equals to C, my temperature raises by 1 unit temperature, 1 Kelvin, 1 degree Celsius. So if I want to raise the temperature by 2 Kelvin, 2 degrees Celsius, I must supply double the amount of heat. So Q is actually directly proportional to change in temperature. If I want to raise the temperature by 10 Kelvin, I have to supply 10 times the heat capacity. If I have to raise the temperature by 100 Kelvin, I have to supply 100 times the heat capacity. So it is related to delta T. C delta T. The symbols I'm using here are important. Heat capacity in itself is, it does not concern itself with the mass of the object. It does not concern itself with the number of particles. It concerns itself with the fact that there is an object present. If I want to raise the temperature by 1 unit temperature, how much heat do I require? And the formula is Q equals C delta T. What does deal with mass is specific heat capacity, which is represented by small c. What deals with number of particles is molar heat capacity, which is represented by C under subscript m. Molar heat capacity, C subscript m. So molar heat capacity, if I were to quickly define it, it is the heat required to change the temperature of 1 mole of a substance. 1 mole of a substance by 1 unit degree Celsius. 1 unit temperature. So it is the heat required to change the temperature of 1 mole of a substance by 1 unit. I can write the formula for this as well. Q equals NCm delta T. So higher the number of moles, more is the heat required. Higher is the molar heat capacity, more is the heat required. Higher is the change in temperature, higher is the heat required. This is one formula that you can remember. When it comes to specific heat capacity, I just have to change this n by mass. So if I have to heat a more massive body, if I have to heat a heavy body, I need more heat. If I have a 100 kg block of iron, then to raise its temperature by 1 Kelvin, I need more heat. If I have a 1 kg block of iron, to raise its temperature by 1 Kelvin, I need less heat. So it's directly proportional to mass. This is wrong. It should be small c. Small c is specific heat capacity. If the specific heat capacity is more, then I need more heat to make the same change. If I want to make higher temperature change, if instead of 1 Kelvin I want to change 10 Kelvin, then I have to supply more heat. Obviously, right? If I want to raise the temperature more, I have to supply more heat. Moving on, equipartition of energy. What an interesting concept. All things have energies. All things have some energy. Even objects at 0 Kelvin, absolute zero temperature, have some energy to them. And equipartition of energy tells us that energy does not discriminate between different modes of energies. What are different modes of energies? I am standing here. How can I express my energy? I can move towards right, I can move towards left. So moving in this direction is one way I can express my energy. I can move towards the camera. I can move away from the camera. I can move towards you. I can move away from you. That's one way I can express my energy. I can go up. I can go down. I can go up. I can go down. That's another way I can express my energy. So 1, 2, and 3. These are translational degrees of freedom. Translational degrees of freedom. So equipartition of energy tells us that amongst all these different ways, the energy partition will be equal. Next thing, how can I express my energy? I can rotate. I can rotate in this direction. I can also rotate in this direction. I can also rotate in this direction. So 3 ways I can rotate as well to express my energy. And these are 3 rotational degrees of freedom. And what does equipartition of energy tells us? That energy will be shared equally between these parts as well. For once, we are going to consider monoatomic ideal gases. A monoatomic ideal gases, single atoms, point particles. Single atoms, point particles. Point particles. Now, I want you to tell me, translationally, moving wise, how many degrees of freedom does it have? And the answer is 3. It has 3 degrees of freedom translationally. How many degrees of freedom does it have rotationally? Can a point rotate? Can a single point rotate? When we talk about monoatomic ideal gases, we don't consider them to have a certain radius. We consider them to be point particles. And what is the radius of a point, by the way? What is the radius of a point? It is 0. If the radius of a point is 0, can it rotate? Can it rotate? The answer is no. It can't rotate, so it only has 3 degrees of freedom. It can go in x direction, it can go in y direction, it can go in z direction as well. 3 degrees of freedom. And what does equipartition of energy say? That in each of these different ways to express your energy, how much energy will be given? It will be 1 by 2 RT. 1 by 2 RT for every mole of your gas. For every mole of your gas. 1 by 2 RT for every mole of your gas. R is what? R is the universal gas constant. Universal gas constant. You know universal gas constant, you must have done certain questions from ideal gas. If you have not, you will come across those questions. It's the universal gas constant. Its values are very clear. In SI units, the value is 8.314. In terms of liter bar, the values are 0.083. In terms of liter ATM, the values are 0.082. So you have to remember the units, but it's a constant at the end of the day. The important thing is temperature. As the temperature increases, the energy increases. Remember how we talked about kids. Kids are crazy, man. Kids are so crazy. I mean, I am sure there are certain people who love kids. And even I love kids, but if you look at them, they fascinate me so much, but they are crazy. I mean, they just run around for no reason whatsoever. I remember being a kid, I used to love running. Not running to something, not running away from something. I used to love running. That's how gas particles are. They just love moving around. They just love doing random stuff. They just like hitting each other. They just like hitting into the walls, right? As temperature increases, the craziness increases. When we are kids, our temperature is higher. When we grow up, our temperature becomes lower. We start moving slowly. We start making decisions. We start having responsibilities. Now we have careers to decide. Now we have to write an exam. Now we have to sit and study for 10 hours. We can't just go and play football. We can't just go and play cricket. We can't just go and hang out at a friend's place playing with Hot Wheels or playing computer games. We have to become we have to become cooler. We have to become cooler, lower temperature. And that's what happens when you raise or lower the temperature of an ideal gas. When you raise the temperature, the energy increases, particles start moving around more. When you decrease the temperature, particles start moving around less. So if in each of these three different ways, in each of these 1, 2 and 3 different ways, 1 by 2 RT is shared, what is the total energy? Total energy is 3 times 1 by 2 RT. 3 times 1 by 2 RT, which is 3 times 1 by 2 RT, which is equals to 3 by 2 RT, which is equals to 3 by 2 RT. This is the energy of an ideal gas. I asked you to remember this formula in the last few lectures, but now you can make sense of it, because in each translational degree of freedom, 1 by 2 RT is shared per mole of the gas, and hence we have 3 by 2 RT in total. 3 by 2 RT in total. I'll do one thing. I'll just write it cleanly so that you can note it down. Ideal gas, right? Ideal gas, 3 degrees of freedom. Degrees of freedom, where can it go? It can go in X direction, it can go in Y direction, it can go in Z direction. 3 degrees of freedom. Each degree of freedom, for each degree of freedom, you have 1 by 2 RT. I want to emphasize this is per mole. This is per mole. So I'll just make a note. Mole inverse, that means per mole. So total U is equals to 3 times 1 by 2 RT, 3 by 2 RT. U is equals to 3 by 2 RT. लिख लो यार इसको, ये बहुत काम आएगा. We are also going to talk about diatomic gases, polyatomic gases. Just take a note of this. Very important formula. It's also going to help us in defining heat capacities later. So just take a note of this. Just take a moment to go through the reasoning of it. Pause the video if you have to. Look up a few more resources if you have to. कोई book पढ़ लो यार, NCERT में से पढ़ लो. कोई और book हो आपके पास, उसमें से पढ़ लो. Very important concept, equipartition of energy. All right. Another point I want to mention over here is this emphasis I put on per mole. What if we don't want to talk about moles? That is the difference between K and R. R we already know, gas constant. R is the gas constant. We use it in case we want to define per mole of gas energy. But simply replace R with K. Simply replace R with K. K is what? K is the Boltzmann constant. K is the Boltzmann constant. A very famous scientist who studied thermodynamics, who studied statistical mechanics. The constant is named after him. K is related to R with the relation that R is equals to K times Na. So what is Na? Na is the Avogadro's constant, 6.022 into 10 raised to power 23. So if you know the value of R, to find the value of K, you just divide R by the Avogadro's constant. So R is equals to Kna. And if you replace this in the formula, if you write U equals 3 by 2 kT, then this is the energy. This is the average energy per molecule of the gas, per atom. We are talking about monatomic. So per atom of the gas. See, thermodynamics can't tell you what is the energy of this particular atom. Thermodynamics cannot tell you about microscopic properties, but it can tell you about average properties. It can tell you on an average all particles have how much energy, and they have 3 by 2 kT in case it is a monatomic ideal gas. We are going to talk about diatomic, polyatomic gases as well, but first try to understand monatomic ideal gases. Alright guys, this is the end of first segment, end of concepts. Revise the concepts before moving on to the applications so that we can solve applications side by side. You can also try solving them. I'll obviously give you the right answer. We'll learn something new. So we'll see each other again in applications.